Imagine a black hole slowly fading instead of living forever.
Most people think black holes only consume, never give back.
But even the darkest objects in space slowly lose energy.
They emit faint radiation born from quantum fluctuations.
Picture pairs of particles forming at the black hole's edge. Visual: two glowing motes appear, one falling inward while one drifts free.
One falls into darkness, the other escapes into the universe. With each escape, the black hole loses a bit of energy. Over unimaginable time, this slow leak becomes significant.
The smaller the black hole becomes, the hotter it grows. Its surface glows from deep red to brilliant white.
This behavior is the reverse of most objects we know.
As it shrinks, its radiation increases dramatically.
Eventually, the process accelerates beyond control. Imagine a cosmic ember flaring brighter before fading forever. At tiny scales, the black hole becomes intensely energetic. When it reaches its final size, the end comes quickly. Its last moment is a burst of powerful gamma light. Then, in an instant, the black hole is gone. No core remains, no shadow, nothing left behind. Even cosmic giants cannot escape the laws of physics. This slow evaporation shapes the distant future of the universe. Imagine the universe trillions of years from now. Only a few isolated black holes remain in the far future.
Each slowly evaporates, leaving a colder cosmos behind.
A black hole with the sun's mass takes enormous time to fade. Its lifetime is millions of times older than the universe itself.
Over human history, such a black hole barely changes.
Yet the rule of evaporation never stops working.
Think of it as the universe's slowest ticking clock.
The mechanism begins at the quantum level.
Time fluctuations constantly reshape the space near it.
These fluctuations create particles that shape the hole's fate.
One escaping particle is enough to drain energy over time.
The black hole slowly shrinks as energy escapes outward.
Eventually, the black hole becomes incredibly small. At that size, it radiates with astonishing power. The end resembles a final flare, bright and brief.
Afterward, space is left perfectly empty and silent.
This evaporation challenges our idea of immortality in space.
Even giants of gravity must eventually fade away.
Their endings remind us everything in the universe has a lifespan. No black hole lasts forever, despite their immense power. The process is slow, but utterly inevitable.
The final flash leaves no remnant behind.
Some scientists call this a quiet death of cosmic titans.
Black hole evaporation shapes the universe's distant fate.
When the last hole dies, cosmic darkness deepens. Every black hole contributes to the universe's cooling.
But the final stage happens with explosive speed.
Think of a candle that burns dimly, then flares suddenly.
Black holes behave similarly near their final moments. The final energy release is pure radiation.
Nothing material survives or escapes this last pulse. Afterward, space-time becomes calm again. The universe hardly notices the disappearance at first. But over immense time, many such endings reshape everything.
Eventually, only cold radiation fills the universe.
This is one possible destiny of our cosmos.
Black holes remind us that even extremes obey physics.
Their evaporation is a triumph of quantum insight. It shows how small-scale physics shapes cosmic giants. The idea connects the tiniest scales with the largest. The process illustrates the unity of physical laws. Even the universal's darkest objects cannot escape change.
Their endings carry a quiet elegance within chaos.
Each final flash marks the closing of a cosmic chapter.
When the last black hole dies, time feels endless.
But today, black holes still dominate galaxies with gravity.
Their long lives shape the formation of stars and worlds. Yet even they will one day fade into quiet light.
Have you ever wondered why full moons rarely enter Earth's shadow?
It seems like eclipses should happen every month, doesn't it?
But the universe rarely aligns things as perfectly as we imagine.
The moon's orbit is slightly tilted compared to Earth's orbital plane.
That tine tilt makes all the difference in eclipse timing.
Earth follows one road, the Moon follows a slanted one beside it. During most full moons, the Moon is simply off the shadow's path. Sometimes it passes above the shadow, sometimes just below. A 5-degree tilt sounds small, but in space, it's significant.
Imagine tossing a ball with your arm tilted just a little. Even a slight tilt sends the ball past the mark. The Moon behaves the same way during most full moons. Full moon doesn't guarantee alignment with the ecliptic plane. For an eclipse, geometry must line up with near perfection. The Moon must pass through one of its orbital crossing points. These crossing points are where lunar and solar planes meet. Only then can a full moon enter Earth's long shadow. Think of these nodes as cosmic checkpoints.
If the Moon reaches a node at the wrong phase, nothing happens.
But when a full moon aligns with a node, the stage is set.
Earth casts a massive shadow, stretching far into space.
The Moon usually flies above or below that shadow.
Only rare alignments send it directly into the darkness.
When that happens, the result is a lunar eclipse. Unlike solar eclipses, lunar eclipses are visible across half the planet.
You don't need to stand in a narrow path to see it. But you still need that perfect alignment to make it happen.
Full moons alone are not enough for eclipses.
Without the node crossing, the Moon simply misses the target. The sky gives us eclipses only when geometry cooperates. Most full moons are just slightly misaligned. That slight misalignment protects it from the shadow. Only a handful of full moons each year hit the right spot. Think of it as two clocks that rarely strike the same second. But when they do, the sky offers something remarkable.
During totality, the Moon turns deep red. A crimson orb hangs above Earth like a burning ember. That red color comes from sunlight filtered through Earth's air.
It's the glow of millions of sunrises and sunsets.
The Moon wears the color of our atmosphere in that moment.
Show happens because the geometry finally lined up.
You're watching a three-body dance performed with precision. But that dance rarely leads to perfect alignment.
Most full moons simply glide past the shadow, unharmed.
Imagine a doorway and an adult East Asian man walking just beside it.
It's the moon, slipping past Earthers' shadow each month. Only when it steps through the doorway do we see an eclipse.
These alignments follow cycles across many months.
The nodes themselves slowly drift along the orbit.
This drift creates eclipse seasons about twice a year. During those seasons, eclipses become more likely.
Outside those seasons, eclipses are almost impossible.
It all goes down to geometry, timing, and that small tilt.
5 degrees keeps the moon out of the shadow most months.
But that same tilt allows eclipses to feel rare and special.
The sky doesn't give us eclipses casually.
It requires the harmony of multiple celestial motions.
When alignment fails, the moon stays bright and untouched.
When alignment succeeds, the sky turns into a theater. Earth's shadow climbs across the lunar surface slowly.
Totality reveals the moon's red, atmospheric glow.
The rare geometry creates a quiet cosmic spectacle. After totality, the moon returns to bright silver light. The shadow retreats, leaving the moon unharmed. Alignment breaks again as the moon resumes its tilted orbit. And just like that, the eclipse ends.
Most full moons never experience this shadowed journey.
But when geometry aligns, the sky turns breathtaking.
Each eclipse reminds us how delicate cosmic alignment is. The slightest shift creates enormous changes in shadow.
Tiny tilts shape the rhythm of our planet's sky.
Even small deviations guide the moon's monthly path.
Without that tilt, eclipses would be monthly and ordinary.
But with it, eclipses become rare events worth waiting for.
The moon misses Earth's shadow far more often than it meets it.
And that is why lunar eclipses are precious moments in the night sky.
Have you ever wondered how a black hole ends its life?
Not while consuming stars, but in its final true moment. A black hole may seem immortal, yet it isn't.
Over trillions of years, it slowly evaporates away. Hawking evaporation drains its mass grain by grain.
When it becomes small enough,
everything changes rapidly. Its temperature rises beyond anything imaginable.
Light shifts into extremely tiny, energetic wavelengths.
At subatomic size, its energy becomes violent and focused.
Imagine watching it from a quiet outpost on Mars.
In the distance, a single dot flares like lightning. That sudden flare is a dying black hole's final breath. The flash lasts only a fraction of a second. It is the universe's briefest, brightest farewell.
This moment is called a gamma-ray burst.
Unlike a supernova, no debris explodes outward.
There's no blast wave, no cloud of ruined matter.
Everything released is pure energy, nothing more.
And after that flash, the black hole is gone forever. No remnant, no shadow, no trace remains.
The universe simply continues, as if nothing occurred.
Nearby space reshapes gently after the hole vanishes. Orbits adjust as the weight once anchoring them disappears. The black hole leaves no cavity behind in spacetime.
Only the memory of its pull remains for a moment.
South Asian female scientists model this end because we can't observe it. Yeah.
Small, ancient black holes evaporated long ago.
Larger ones will outlive countless future civilizations. But eventually, every black hole meets this final moment. In its last stage, energy release becomes extreme.
Radiation intensifies as the hole shrinks rapidly.
The countdown accelerates until no time seems to pass.
The final burst is unimaginably powerful. Yet it ends almost before it begins. That spark is the universe releasing tension built for ages.
And then, just serenity. Quiet space with no scar left.
Black holes remind us that even cosmic titles end. Nothing in the universe escapes change forever.
Their final moment is brief, yet deeply symbolic.
It marks the last release of stored cosmic energy. Then all that remains is calm, stable spacetime. Imagine the far future when many black holes vanish. The universe becomes quieter with each disappearance.
Eventually, only occasional gamma flashes break the silence. These flashes are like the universe's final sparks.
One day, even those last black holes will evaporate.
After the last one fades, darkness grows complete. Space becomes a cold, quiet ocean without giants.
But right now, black holes still shape galaxies. They guide the motion of stars and cosmic gas. Their gravity sculpts structures across the universe.
Yet even these giants will one day burn out. Their long, slow fade leads to one brilliant finale.
That finale is a gamma-ray flash, swift and pure. It's the brightest light the universe can produce.
But brightness doesn't mean longevity. It ends instantly.
Afterward, space feels strangely peaceful.
The absence of the black hole barely changes the universe.
Yet its final flash tells a quiet, profound story.
The universe rewrites itself after each disappearance.
Think of the blackout as a cosmic breath exhaled.
The last flash marks the end of a Titan's influence.
Gamma bursts become the final signatures of black holes.
In those distant ages, black holes will be rare memories.
Their endings are quiet, but filled with significance.
They remind us, even the strongest structures fade.
A dying black hole ends with nature's brightest light.
That light is its last message to the universe. And in the next instant, there is nothing left. No debris, no fragments, not even dust remains.
Only the memory of that flash lingers in thought.
The universe absorbs the moment and moves on.
Have you ever wondered if something outside our universe is pulling on us? It's a bold idea, but it doesn't match what we observe.
Some imagine another universe tugging from beyond our view.
But gravity never grows stronger with distance.
Gravity weakens the farther two objects are separated.
Imagine trying to pull a boat across an ocean with a long rope. The farther the boat is, the weaker your pull becomes.
An external universe would work the same way.
Its gravity would diminish, not accelerate our expansion.
But the universe is accelerating faster over time.
That behavior doesn't match an outside gravitational tug.
Gravity pulls inward. Dark energy pushes outward.
And dark energy grows stronger with more space, not less. Imagine every cubic inch of space generating a tiny push. As the universe gets bigger, the total push increases.
An outside pull cannot explain this runaway expansion. If something were pulling us, one side would stretch faster.
But acceleration appears uniform everywhere we look.
That uniformity is the signature of dark energy within spacetime.
Think of space acting like rising dough, pushing raisins apart.
No hand stretches the dough. It expands from within.
Dark energy works the same way, not from outside, but inside.
It fills the fabric of the universe like a quiet pressure.
But dark energy becomes more dominant as space grows.
The bigger the region we examine, the stronger dark energy acts.
This is opposite of what gravity does across distance.
Imagine two stars drifting farther apart. Their pull weakens. Now, imagine empty space between them, increasing in pressure. That's dark energy. Not a pull, but a push. Some call it vacuum energy, others a cosmic field. Whatever it is, it doesn't behave like gravity.
An external pull would create a directional distortion.
But we see no such tilt in cosmic expansion.
This uniformity rules out an outside gravitational cause.
Dark energy behaves like a property of space-time itself.
It acts evenly through every corner of the cosmos.
Think of space as a quiet engine, constantly running. That engine grows stronger as the universe expands. An external universe cannot power that engine.
Its gravity would fade long before reaching us.
Dark energy, however, grows with the size of space.
The more universe you have, the more dark energy you see.
Imagine inflation happening slowly, continuously.
Not from edges, but from every point in the universe.
This is why the outside pull idea collapses under evidence.
Dark energy acts everywhere, not from a single place.
Even distant galaxies feel the same accelerating push.
That push is built into the vacuum of space. Gravity alone cannot produce accelerating expansion.
It can slow expansion, but never speed it up.
Dark energy does the opposite. It speeds expansion relentlessly.
As space grows, dark energy grows with it.
No external pull can mimic this behavior. Dark energy has no direction. It acts isotropically.
A pull would have a direction. A push fills all space.
The acceleration we observe lacks any preferred direction.
This is one of the strongest clues we have.
The universe expands like rising bread, everywhere at once.
No external hand stretches that dough. Expansion radiates from internal points, not distant edges.
Dark energy fills the dough. It is the expansion.
Eventually, distant galaxies will slip beyond visibility.
Space ice will grow too fast for light to cross. Not because something pulls them away.
But because space itself pushes them apart.
Dark energy is not external. It's intrinsic. Whatever its true nature, it lives within space-time. And it shapes the universe from the inside out. No outside universe pulls us. The engine is internal. Dark energy defines our future cosmic horizon.
It drives the universe toward isolation and silence.
Yet its origin remains one of science's deepest mysteries.
But one thing is clear. It isn't an external pull. The universe expands from its own fabric, not from beyond it.
Have you ever wondered why solar eclipses are so hard to see?
They feel rare because their shadow touches only a narrow path. Some imagine another universe tugging from beyond our view. But gravity never grows stronger with distance.
Solar eclipses feel rare because their shadow is incredibly narrow.
Move slightly away, and the eclipse vanishes instantly.
Lunar eclipses, however, share their beauty with half the planet.
They are far more generous than solar eclipses.
Solar eclipses invite a few. Lunar eclipses welcome millions.
This contrast comes down to pure celestial geometry.
The moon is small, so its shadow on Earth is tiny.
Earth is huge, so its shadow easily covers the moon.
The light bends around the edges, but right here, it creates a perfect silhouette. It's just a small coin, but the shadow is massive.
That's the solar eclipse. Small object, small shadow. Now picture Earth casting a truly massive shadow. The moon slips into that shadow with ease.
Lunar eclipses can be seen from the entire night side. Solar eclipses make you chase the shadow. Lunar eclipses simply meet you where you are.
Many people don't realize solar eclipses happen more often globally.
They just rarely visit the same place twice.
Lunar eclipses are fewer but seen by more people.
Solar eclipses feel like exclusive celestial events.
Lunar eclipses feel like shared cosmic moments.
The sun, Earth, and moon must align perfectly for both. But the viewing conditions differ entirely.
Solar eclipses require standing in the right tiny spot.
Lunar eclipses require nothing more than nightfall. During a solar eclipse, day turns into sudden twilight.
Temperatures drop, winds shift, and silence deepens.
Totality feels intimate and fleeting.
Lunar eclipses feel calm, almost meditative.
Solar eclipses last minutes. Lunar eclipses unfold patiently.
Shadow size explains everything.
The moon's shadow is only dozens of miles wide.
Earth's shadow spans thousands of miles. From space, Earth easily darkens the moon.
But the moon barely darkens Earth.
That precision makes totality rare for observers. Step a few miles aside, and totality is gone. Lunar eclipses don't need precision at all. They invite half the planet to witness them.
Solar eclipses whisper, "Come, find me."
Lunar eclipses answer, "I'll meet you anywhere."
Solar visibility depends heavily on location. Lunar visibility depends only on being in darkness. During totality, the sun becomes a cosmic jewel. During a lunar eclipse, the moon becomes a red lantern.
One event feels dramatic and sudden.
The other feels serene and atmospheric.
Both reveal the precision of celestial mechanics. Slight differences in alignment create huge differences in experience.
A solar eclipse is nature's narrow spotlight. A lunar eclipse is nature's shared lantern.
Remember, solar eclipses happen more often globally.
But personally, you may witness only a few in a lifetime. Many shadow paths miss densely populated areas. Lunar eclipses are rarer, but widely visible.
They reward anyone who simply looks up.
Eclipses show how geometry shapes our skies.
They reveal the cosmic dance we live within.
Solar or lunar, each eclipse carries its own wonder.
And every eclipse reminds us to pause and look upward.
Have you ever wondered whether the Big Bang was a black hole exploding? It's a fascinating idea, but the physics tell another story. To understand why, we must ask how black holes really die. Black holes don't explode with stored matter.
Instead, they slowly leak energy over unimaginable time.
This gentle leak is called Hawking radiation.
Imagine an ice cube melting molecule by molecule.
A black hole fades the same way, just far slower.
After trillions of years, it becomes smaller than an atom. Only then does it release a final flash of gamma light.
That flash is brief, gone before you could blink.
And after that moment, the black hole is simply gone.
A black hole's death is quiet, not violent. Now compare that with the beginning of the universe.
The Big Bang wasn't an object exploding in space. The Big Bang created space and time as it expanded.
Imagine the surface of a balloon inflating everywhere at once.
The universe grew the same way, internally, not outward.
A black hole cannot create that kind of expansion.
It releases energy, but not new spacetime.
Big Bang expansion isn't matter bursting outward.
No explosion pushes galaxies. Space grows between them.
Black holes never behave like that. Their final flash is tiny compared to cosmic scales.
The Big Bang, however, filled the universe with light. It set temperature, motion, and structure in motion. If you were there, you wouldn't see an explosion. You'd see space itself stretching faster than light. That expansion didn't come from any dying object. It came from everywhere simultaneously. Black holes don't store universes inside them. They warp space, but don't release new cosmos. Material falling in doesn't stay intact inside. It becomes part of space-time's structure, not stored matter. When the black hole evaporates, nothing pops out.
Just information radiated slowly as faint energy.
The Big Bang didn't radiate slowly. It ignited instantly. It launched a universe full of particles, energy, and motion. Black holes end in silence. The Big Bang began in fire. One is a fading ember, the other an ignition. Think of a match burning out versus a star being born.
A black hole's end returns energy to emptiness.
The Big Bang created everything that would ever exist.
Even space-time itself emerged from that moment. No black hole has ever shown that behavior.
So the Big Bang wasn't something escaping a dead black hole. It was the fundamental beginning of physics as we know it. Imagine the difference between whispering and shouting.
Black holes shrink, the universe grows.
Their roles in nature couldn't be more different.
Black hole death is the end of curvature. The Big Bang was the beginning of curvature.
One marks a conclusion, the other a creation.
Black holes do not explode into new universes.
And the Big Bang wasn't the remains of something dying.
It was the origin of matter, not the escape of matter.
The universe didn't spill out, it turned on. Think of a room where the walls move apart instantly.
Closer.
Space wasn't a container, it was the creation. And time began at that same moment.
Black holes cannot trigger time's beginning.
They end with a whisper. The universe began with a roar.
Confusing the two misses the beauty of each process.
One fades into the fabric of space.
The other creates the fabric of space.
So the Big Bang was not a black hole exploding. It was something far more profound. It was the beginning of everything we measure today.
And nothing in a black hole's death resembles that.
The universe didn't escape a dying object. It emerged anew.
Have you ever noticed the sun rising in a slightly different spot each month?
It's not the sun moving around us. We're the ones in motion.
Imagine Earth on a giant racetrack circling the sun.
As we move, our view of the sun slowly changes.
Each month, we face a slightly different patch of sky.
This creates the sun's slow glide through the constellations. Ancient astronomers called this motion the Zodiac.
Today, we call it the Ecliptic, the sun's annual path.
You can't see the stars behind the sun during the day.
But if you could dim the sun, the constellations would appear.
Every month, the sun stands in front of new constellations.
This steady drift shapes how we read the sky.
Think of it like changing seats in a giant theater.
The sun stays still, but our moving vantage point shifts its position.
This motion affects more than sunrise and sunset points.
It also guides where planets appear in the sky.
Most planets orbit in roughly the same plane as Earth. That's why they never stray far from the ecliptic.
Even comets often follow this cosmic highway.
The sun's monthly shift
is a silent engine of sky patterns.
It's the reason certain constellations belong to each season.
Summer reveals one background of stars, winter another.
This cycle repeats year after year, unchanged.
The ecliptic is more than a line. It's the spine of the sky. When that crossing aligns perfectly, we get an eclipse. Most months, the moon passes slightly above or below it. That tilt explains why eclipses don't happen monthly. All of this begins with Earth's motion around the sun. Every degree we move changes how the sun appears. Sometimes it rises farther north, other times farther south. The shift is small daily, but obvious over months. This slow change shapes the length of daylight.
It even defines our seasons.
Summer brings higher arcs. Winter brings lower ones.
The sun's monthly drift is like a celestial calendar.
Early civilizations used it to track time and agriculture.
Sailors navigated using the sun's seasonal position. Today, astronomers still rely on this solar path.
It keeps the sky organized, predictable, and structured. The ecliptic shows the sun's true journey through space.
And it anchors the motion of planets around it.
The sun doesn't wander randomly. It follows a precise path.
We only see the shift because Earth keeps moving.
Think of it like circling a lamp in a dark room.
The lamp never moves, but your perspective changes.
The sun behaves exactly like that lamp.
Each month offers a new cosmic viewpoint. You're riding a planet in constant motion. This motion turns the sky into a living, shifting map. The sun's position marks our place on that map.
By watching it, you can read the rhythm of Earth itself.
Every sunrise angle tells you where we are in orbit.
Every sunset confirms Earth's journey around the sun.
The sun's monthly drift is slow but precise.
Astronomers map this drift with exact measurements.
But you can observe it with nothing more than your eyes.
Just notice where the sun rises today.
Then check again next month. You'll see the change.
This is celestial mechanics made visible.
Orbiting while spinning, creating layered motion. That motion shapes everything we see in the sky.
Without it, seasons and sky patterns wouldn't exist.
The sun's steady drift binds our year together.
It's the quiet metronome of our cosmic journey.
Every month, the sun stands before new stars. That procession is the foundation of the ecliptic.
And the ecliptic shapes nearly all celestial motions we observe. So when the sun shifts, you're witnessing Earth's orbit.
You're watching our planet move through the cosmos.
The sun simply marks our changing viewpoint.
This monthly shift connects us to ancient sky watchers.
It reminds us we inhabit a world that never stops moving.
The sky is a living story, written in light and motion.
And each month, the sun turns a brand new page.
Have you ever wondered why dark energy grows stronger as the universe expands?
It sounds mysterious, but the idea is surprisingly simple. Dark energy isn't a force pushing from outside the universe.
It is a property of empty space itself.
Imagine every cubic inch of vacuum containing tiny energy.
More space means more vacuum, and more vacuum means more dark energy. That's why dark energy becomes more noticeable as space grows.
This effect is built into the structure of spacetime. Nothing pushes from outside. Space stretches from within.
The universe inflates the same way, uniformly across all directions.
Dark energy acts like a pressure emerging from emptiness.
The more emptiness exists, the more influence dark energy has.
It doesn't dilute like gravity or magnetism.
Instead, dark energy stays constant per unit of space. So when space increases, dark energy collectively increases too.
This explains the accelerating expansion of the universe.
The universe expands faster because there is more space to expand into itself.
It's a self-reinforcing process built into the vacuum.
No external galaxy could cause this acceleration. Gravity weakens with distance, But dark energy does not.
If something pulled from outside, expansion would slow with distance.
Instead, expansion accelerates the farther out we look.
Picture a rubber sheet being stretched evenly from within. No hand pulls its edges. It expands everywhere at once.
Dark energy behaves like that internal stretching. Light waves follow the flow of an expanding field.
It acts uniformly across the universe, large or small.
In fact, voids are where dark energy's influence dominates. Galaxies cluster less tightly as dark energy rises.
This is why the universe looks more stretched today than in ancient times.
Billions of years ago, gravity ruled over expansion. Today, dark energy outpowers gravity on the largest scales. And in the far future, this trend will grow even stronger.
More space means more vacuum, and thus more dark energy.
Some call this a cosmic runaway expansion.
But it's not chaos. It's built into the fabric of reality.
Dark energy acts like a constant background pressure.
It's subtle locally, but immense on cosmic scales.
You won't feel it on Earth. Gravity overwhelms it.
But between galaxies, dark energy becomes the dominant force. Empty regions grow faster than star-filled ones. Its influence grows wherever emptiness grows.
This is why distant galaxies accelerate away from us.
They aren't moving through space. Space is stretching.
It's like dots on a balloon drifting apart as it inflates.
No dot is pushing. The surface itself is growing.
Expansion comes from the vacuum, not from objects.
Dark energy is woven into that vacuum. The more vacuum we have, the more dark energy operates.
This is the opposite of any external pulling force.
External forces weaken with distance. Dark energy grows with scale.
The universe behaves as though expansion is its natural rhythm. Dark energy is that rhythm made visible.
It increases not because of movement, but because of volume. When the universe doubles in size, vacuum doubles too.
This is why expansion speeds up rather than slow down.
It's a feedback loop built into the universe.
Dark energy doesn't push, it accumulates.
The larger the universe becomes, the stronger its pull outward.
Matter will drift apart until darkness dominates.
In the end, expansion itself may be the only motion left.
All of this emerges from the simplest idea. Vacuum holds energy.
And as vacuum grows, that energy becomes more influential. Dark energy is not an external force. It is space itself.
The universe grows, so dark energy grows with it.
Empty space becomes the stage where expansion accelerates.
The more space you create, the more expansion continues.
Dark energy transforms emptiness into a dynamic engine.
And through it, the universe keeps accelerating into the future.
Have you ever wondered what remains after a black hole dies?
Most imagine a deep cosmic hole left behind. But the universe doesn't keep scars from black holes. When a black hole evaporates, nothing unusual remains. No hollow cavity forms where it once stood. There is no sinkhole, no lingering darkness.
The black hole's disappearance is surprisingly quiet.
The fabric of space behaves exactly that way.
During evaporation, mass escapes as pure radiation.
Nothing bursts outward when that point disappears. No shockwave forms, only stillness fills the void. Black holes do not store pressure like stars do.
There is no explosion waiting inside.
A black hole collapses inward, not outward.
Even its final flash leaves no crater behind.
The space simply becomes ordinary space again.
Imagine a candle flame disappearing without altering the air.
A black hole ends with that same gentle simplicity.
There is no leftover tunnel or hidden opening.
When curvature disappears, nothing remains.
Space remembers nothing after a black hole ends.
No measurable structure marks where it existed.
It doesn't leave a vacuum deeper than surrounding space.
Even nearby stars feel no sudden change. Gravity fades gradually, not abruptly.
The universe transitions gently through the final moment.
Think of ice melting without leaving a hole in water.
A black hole disappears with the same natural ease.
Space-time relaxes once the mass is fully gone. No leftover energy blast marks its location.
Only radiation escapes during the long evaporation.
Afterward, the universe looks perfectly untouched.
Nothing remains to signal that a giant once stood there. The spot becomes indistinguishable from anywhere else.
Some imagine a vacuum bubble left behind. But vacuum is the same everywhere once curvature ends.
There is no depression or leftover gravitational dip. Space behaves elastically, restoring itself fully.
The black hole does not punch a permanent scar.
It simply loses mass until nothing remains.
The final flash is brief and quiet.
After that, the region is perfectly ordinary. No ripple of pressure spreads outward.
No trail of matter appears after it ends.
Even its last moment leaves no disturbance.
Space heals instantly because there is nothing to heal.
A vanished black hole leaves only calm emptiness. Picture a shadow disappearing when the light shifts.
The black hole's end is just as seamless.
No memory of its gravity persists afterward. All curvature vanishes when its mass evaporates.
The universe behaves as if nothing extraordinary happened. Even the final burst leaves no structural trace.
It's a quiet exit for something unimaginably powerful.
The space it occupied returns to perfect normalcy.
Imagine tension lifting from a stretched surface.
That is how space-time reacts as the black hole fades.
The universe has no leftover hole to fill. Everything simply returns to equilibrium. The black hole was temporary. Space is permanent. Once it's gone, nothing unusual is left behind. The end feels anticlimactic, but profoundly elegant. Space closes smoothly where the horizon once stood.
No boundary marks the place anymore.
All that mattered was the mass. Without it, the drama ends.
Nothing pulls, pushes, or erupts after disappearance.
The universe simply continues without the black hole. The site becomes just another patch of cosmic quiet. No trace tells future astronomers what once existed. The black hole ends, but space-time carries on smoothly. In the end, the universe leaves no mark of its passing.
Have you ever wondered why eclipses don't happen every month?
Full moons and new moons happen monthly, yet eclipses don't. The secret lies in the moon's tilted orbit. Imagine the moon circling Earth on a slightly slanted track. Most months, the moon misses the shadow entirely.
During new moons, its shadow often misses Earth completely.
During full moons, it usually passes above Earth's shadow. Alignment must be perfect for an eclipse to occur.
That perfect line is surprisingly rare.
The moon's orbit is tilted about 5 degrees. These crossing points are called nodes.
An eclipse requires the moon to reach a node at the right time.
Most months, the moon reaches the node too early or too late. Only when timing matches perfectly does an eclipse begin. These rare alignments create eclipse seasons. Eclipse seasons happen only about twice a year. Between these seasons, geometry simply doesn't line up.
Imagine two loops crossing like the links of a chain.
Eclipses occur only where those loops meet. A solar eclipse needs the moon at the node during new moon. A lunar eclipse needs the full moon to hit the node precisely. Anything slightly off, and the event disappears. That's why eclipses feel rare and meaningful. The sky must cooperate with extraordinary precision. Think of it like threading a needle while the needle moves. The moon moves fast, and alignment windows are tiny.
Most months, it glides just above the perfect target.
Or it drifts just below where the shadow should fall. Only in rare moments do shadows touch. You must stand in the shadow's exact track to see it.
Lunar eclipses, however, can be seen across half the Earth.
Yet both require the same perfect alignment.
The moon's tilt prevents monthly eclipses. A tilted orbit lifts the moon above the ecliptic path.
Without that tilt, eclipses would happen every month.
The sky would be filled with constant shadows.
Instead, the tilt adds just enough complexity.
This small angle keeps eclipses extraordinary. Picture Earth orbiting the Sun like a giant track.
Now picture the moon orbiting Earth on a tilted loop.
Eclipses only happen when both loops intersect.
This crossing repeats every 6 months.
That rhythm, that rim creates the pattern of eclipse seasons.
These seasons shift slightly each year.
They follow a natural cosmic cycle, lasting 18 years. Astronomers call this the Saros cycle.
It predicts when future eclipses will occur.
But even with perfect prediction, alignment remains rare.
Every eclipse is the result of exquisite geometry. Celestial bodies align like precise pieces of a cosmic machine.
The moon must be at the exact node at the exact moment. A few hours off, and the eclipse vanishes from possibility. These near misses happen every month.
Only at the right crossing do shadows interact.
Solar eclipses need even more accuracy.
The moon's shadow is narrow, only a few hundred kilometers wide.
That's why people travel great distances to see one.
Meanwhile, lunar eclipses share their beauty widely.
Yet both depend entirely on the moon's orbital tilt.
That tilt is the quiet architect behind eclipse rarity.
The sky must align perfectly, and nature rarely obliges. Eclipses reward us with moments of cosmic precision.
They remind us, geometry rules the sky.
The Earth, Moon, and Sun must perform a flawless dance. Twice each year, they hit the perfect formation. Those are the rare windows we call eclipse seasons.
Outside those seasons, alignment simply cannot happen.
That's why monthly eclipses are impossible.
Instead, eclipses are special events born from perfect timing.
Their rarity makes them feel almost miraculous.
The moon must be at the node during new or full moon. Only then does the shadow cast exactly where it should.
That's why eclipses captivate us so deeply.
Rare alignment creates one of nature's greatest shows.